So welcome everybody, and we are delighted to welcome Professor Wenwu Wang from the University of Surrey, who will present the talk Audiovisual Speech Source Separation. Wenwu is a professor in signal processing and machine learning, and she's also an I Fellow at the Surrey Institute for People-Centered Artificial Intelligence. His current research interests include signal processing, machine learning and perception, artificial intelligence, machine audition, listening, and statistical anomaly detection. He has authored and co-authored over 300 papers in these areas. He has been recognized as an author and co-author or a recipient or co-recipient of more than 15 awards, including the 2022 IEEE Signal Processing Society Young Author Best Paper Award, ICAUS 2021 Best Paper Award, DCASE 2020 and 2023 Judges Award, DCASE 2019 and 2020 Reproducible System Award, and LVA-ICA 2018 Best Student Paper Award. Wenwu is an associate editor since 2020 for IEEE ACM transactions on audio, speech, and language processing. He was a senior area editor between 2019 and 2023, and associate editor between 2014 and 2018 for IEEE transactions on signal processing. He's the lecture chair currently of IEEE Signal Processing Society Machine Learning for Signal Processing Technical Committee, a board member of IEEE SPS Technical Directions Board, the chair and the vice chair of the EuroSIP Technical Area Committee on Acoustic Speech and Music Signal Processing, an elected member of IEEE SPS Signal Processing Theory and Methods Technical Committee. In the past, Wenwu was a satellite workshop co-chair for Interspeech 2022, a publication co-chair for IEEE ICA SSP 2019, local arrangement co-chair of IEEE MLSP 2013, and publicity co-chair of IEEE SSP 2009. He's a satellite workshop co-chair for the current IEEE ICA SSP 2024, special session co-chair of IEEE MLSP 2024, and technical program co-chair of IEEE MLSP 2025. And without any further delay, the floor is yours.
Thank you so much, Anna. And sorry, I should have give you a shorter.
No, it's absolutely impressive.
Yeah, thank you so much for the invitation. And it's my great pleasure to speak here about some of our work on audiovisual speech source separation. My background is on signal processing and machine learning. So this is the work actually I have been doing, especially speech source separation I've been doing since probably 20 years ago. And some of the work here I present here today might be a little bit old, but you know, we also have some update about the recent development in this area. So here's the outline of my talk. I will start with this cocktail party problem. What is cocktail party problem, and how speech source separation is related to this cocktail party problem, and especially our earlier work in this domain is mainly using audio-only measurements. I give you some brief idea about these technologies like blind source separation, in-hand component analysis, this is statistical method. And then we also have this computational auditory scene analysis and time friction masking, and sparse representation and dictionary learning techniques. And then the second half of my talk will be on audiovisual method for speech source separation by integrating video signals to enhance speech separation. So we also discussed how to model the audiovisual coherence, the relationship between audio and video sequences. And we will also cover some of the recent development and just give you some idea about what the community are doing right now in this area. And finally, we will summarize the talk and also discuss potential future work. So cocktail party problem. So this problem was actually coined by Professor Colin Cherry. Colin Cherry was a professor in Imperial College, and I think this term was used by him in 1953. The problem is described that human has the ability to understand a particular conversation in a very noisy cocktail party environment where you have many people are chatting, background sound and music played in the background as well. But it seems to be very challenging for a machine to replicate the similar ability. How a machine can understand a single conversation, but muting or ignoring all the other background conversations or noises from the background. So that's the problem we call it cocktail party problem, and how actually human understands sound from a mixture of multiple sound. So this problem, even though it has been described or proposed for many years now, but so far, still you could somehow say no machine has been constructed to do just that, because especially in the very complex acoustic environment, then understanding a single conversation from a mixture of multiple sound is still very challenging, especially for machines. So here we are talking about how to create a machine that is able to understand complex acoustic mixtures or complex acoustic scenes. So if we want to study this problem, then we would have to encounter multiple issues here. For example, one is how many speakers are there and where are they in the room and in the environment. So this is to do with localization and tracking for speech sources, for example. And who speaks and when, this is also studied for many years by speech community, and this is called degradation, and who speaks and when. Yeah. And if multiple people are talking simultaneously, then we will have this speech separation problem. And of course, if we are also interested in what the speaking, then this is a automatic speech recognition problem, right? So of course, sometimes we're also interested in the environment, for example, what the environment look like. This is to do with acoustic scene recognition and event detection. Sometimes when you're talking, you have some other acoustic event in the background. For example, dog barking. If you're in an outdoor environment, you have bird singing and some other sound events. And of course, noise. What type of noise is in the background? Sometimes we'll have to do this categorization. So there's a lot of issues surrounding this cocktail party problem. But here we're going to talk about is mainly on speech separation. So speech separation is about separating the individual speech sources from a mixture or multiple mixtures of multiple speech sources, right? If people are talking simultaneously, can we actually separate the individual speech sources from the mixtures? There are a lot of methods that have been developed in the literature, and because the problem has been studied for probably 30 years now. Speech recognition has been studied more than 50 years now. So this problem is also studied a long time ago. There are methods already developed there, for example, beamforming, which is using the spatial diversity in the microphone array. For example, you can use time delays. You can actually create beams towards the speech sources. Adaptive filtering, this is more to do with speech enhancement techniques, where you could actually treat the other sound as noise, right? You can then use some speed enhancement techniques, but either you could use adaptive filtering. You could use other techniques as well. Blind source separation and independent component analysis is based on statistical method, which we will discuss a bit more later. Sparse representations, matrix factorization, or tensor factorization. This technique is based on manipulating of these, some mixtures matrix and also the mixing matrices and the relationship between them. So we will not discuss today. Computational auditory listening analysis is based on humans' understanding about sound. This is developed in the auditory listening analysis community. It's more like psychology people are more really interested. I think there's a book about auditory listening analysis by Professor Wang from Canada. I think he died only recently. There's also learning-based techniques, especially machine learning. Another topic is using additional information from other modalities, for example, video signals to enhance the separation quality for audio signals. So that's audiovisual speech separation that we will also discuss. So here, first, the techniques that's dated back to probably early 1990s. Actually, it's called blind source separation or independent component analysis, where you have, for example, microphone signals which you capture the sound. This is the X1 to XM microphone signals. And these are the speech sources which are unknown because we don't know how many speeches. Of course, in this particular scenario, we assume we know how many speech sources are there. But you don't know how these speech sources are mixed together. How the speech source is propagated from the source position to the listener position. Here, listeners means that the microphone signals, right? So the problem now is how to estimate the unknown speech sources, given the only information about the microphone signals captured by the listener. So we don't know how they mix together, right? How they propagate together. So if you model this using a toy model, this is a toy model where you have the microphone signals X, then this is the unknown speech sources. Okay. This is the mixed matrix. When we say toy model, it means that we ignore many other things. We just say, okay, these sources are added together, weighted together, right? And we generate the mixtures, which is the microphone signals. But actually, if you want to really precisely model how the speech source is propagated to the listener position, then you would have to consider the room acoustics, right? It's not just as simple as that, like using this linear system. This is the linear system. We know that if H is known, then we can potentially estimate the unknown sources as based on the observations X, right? So the linear systems, for example, if H is a full rank, let's say it's a squared matrix, we can just multiply the inverse of H on both sides of the equation, we will get the S, right? But the problem here is that we don't know H, right? And we also don't know S. So this is a year post problem. You cannot directly solve the problem, right? So the earlier method is based on so-called statistical independence, where we assume that the sources are statistically independent. So we could use for example, a mixed matrix. We multiply these mixtures. Then we just look at whether these estimated signals Y1 to Yn are statistically independent or not. So we can actually use some kind of independence measures in statistics, like high-order statistics, like kurtosis, fourth-order statistics. We can measure whether these signals are statistically independent. If they are not independent, then we can come back to adjust the matrix W until the algorithm converges, where we have the signals which are statistically independent. Right? This is actually also based on this so-called central limit theorem. Actually, if you put a lot of signals together, then the distribution will be towards Gaussian. Actually, if you have different distributed signals added together. So that's the basic idea. So in the room environment, we actually use a little bit more complex model where we have, we are using so-called convolution rather than just multiplication. Convolution means that we have time delays. If you write equation like this, right? So this is the source signal. We have some time delays, which model the propagation, the sound reflection from the room surfaces. Actually, of course, depending on how reverberant the room is, so we might have to use a very large P to count for very reflective room. Actually. So that's in reality we are using a bit more complex model like this, and then actually to estimate the sources as from the microphone signal X, then we have to to be able to identify the mixed matrix and also to estimate the original sources by performing the inverse filtering. So actually here there's a lot of details there, but maybe I should give you just a basic idea used in the community where we can actually convert the convolution into so-called frequency domain by using Fourier transform or discrete Fourier transform. We can actually convert the sound mixtures into frequency domain at each frequency beam or each frequency point, or something we call frequency band. Right? Each frequency band we perform separation. And then we get individual frequency component, which is a source component. Of course, this is just the visualization. Essentially, it's not like this. But basically, at each frequency point, we have a source component separated using some kind of independent component analysis techniques. And then we can actually finally, we need to group them together to individual sound sources. But because here we have a multiple frequency component, right? But one of the issues here is if we go back to the model we just described here, there's inherent uncertainties here or indeterminacies because this ear post problem. So the best we can get is a permutation matrix times diagonal matrix multiplied by the original source. So which means that because of the ambiguities of the model, we don't have we don't know H, we don't know S, right? If you multiply H by a scalar, and you can actually divide S by a scalar. So which means the best you can estimate is there's always a scalar ambiguity. And of course, there's also permutation ambiguity, which means that the order of the sources you reconstructed might be different from the original order. For example, Y1 to Yn, here is the same order, but maybe these signals you estimated might be corresponding to Sn, rather than S1, right? So this is we call permutation ambiguity. So that's because of the ambiguity of the model. So there are too many unknowns here. So that's why we see here the order of the source reconstructed from each individual frequency beings might be random. It could be this one S1, it could be S1, S2, this might be S2, S1, or this might be S2, S1. Right? So when we actually reconstruct the original source back to the time domain, we would have to group these individual source components together to reconstruct the original speech sources. Right? So how to do that? This is what we call permutation problem. So there's a permutation ambiguity, and then we have to actually address that. There's a lot of techniques doing that. One of the techniques is looking at the spectral envelope and the shape of these components, see how similar this one with this one and this one. If this one is, for example, similar to this one, then we say, okay, this is belonging to the same source. So there's a method doing that. So probably don't go into much details, but just to show you a demo that this is the sound mixtures For example, we have the sound mixture.
Die Fronten im Streit den Lauschangriff bleiben weiter starr. Die Union begann in Bonn erneut.
So here we have two speech sources actually. If we use the techniques we just described, you can do that to see this how good it is.
Die Fronten im Streit den Lauschangriff bleiben weiter starr. Die Union begann in Bonn erneut.
You can see that the other sound sources now is you just remove actually. Actually we separate both. This is the other one.
Auf der ganzen Linie siegten gestern die Gegner der Rechtschreibreform vor dem Verwaltungsgericht Hannover.
Yeah, you can see that we can separate them actually. Of course, depending on how complex the mixture is. In this case, these two are efficiently mixed together. Now we have a real room mixture. This is recorded in a real room where you have these surface reflections, right?
So I'm here in my hotel room making some recordings. In the background you hear the TV, which can be pretty annoying. So I have to record 15 seconds and see how well it separates my voice out of those
So here you have a TV, right? Playing sound, and then you have a guy who is speaking. Basically, is reading some script on the book. And then now we can separate them to see.
So I'm here in my hotel room making some recordings. In the background you hear the TV, which can be pretty annoying.
So that one is the speech actually from the one who is reading book. This one, the other one is from TV. Yeah, this is a TV sound actually. Of course, this is a long time ago, but we have a much better result from the state-of-art systems. So this is the method based on statistical models, using ICA by looking at the statistical independence essentially, or we call it decorrelation between the speech sources. So another very popular method is based on auditory scene analysis. Is motivated by psychology study actually, and how human really understand sound. So there's auditory scene analysis. They developed this theory where they say, okay, the sound actually there's a complicated process in the human brain where it performs segmentation and grouping. The segmentation essentially is to decompose the acoustic nature into small elements, sensory elements. And then the grouping process is try to combine the segments into groups so that they can actually generate the individual source streams. What you really hear is the individual source stream from individual speech sources. But it's a complicated decomposition or segmentation process and as well as grouping process. And one of the advantages for this method is that you could actually even work with the single channel sound, or using a single microphone. You just actually analyze the time and the frequency patterns of the microphone signals. In this case, that even you don't have a special information like from multiple microphones, you could still perform separations. And the computational auditory scene analysis is essentially the method actually developed by computer science scientists. They try to actually create some computational models which is able to simulate the auditory scene analysis process, like the segmentation and grouping. They actually try to develop these models. It could be feature-based approaches, or could be other models based on, for example, hidden microphone models or Gaussian mix models. So these type of models where we analyze each time frequency point of the sound mixtures, and then they determine which time frequency point should be belonging to which source. So this is the information they are using is, for example, the harmonic structure in speech signals, the pitch information, how they change with respect to time, or common amplitude modulation, the envelope of the speech signals they evolve with respect to time. That's the key information we often use when we try to figure out which time point of the sound mixture belonging to which speech sources. And the challenges is that how to model, for example, in the unvoiced part of speech, and of course, even for pitch tracking from the noisy speeches is also a very challenging problem. And dealing with the room reversion is also another challenge. So one of the very simple idea from these areas called binary mask, where using this, this kind of models, computational audio signal analysis models, you can actually figure out in the time frequency, in the time frequency condition of the mixtures, each time frequency point, T and F, whether it's belonging to the target sound or is it belonging to the interference sound or the noise. If you only have the two signals, you can actually compare which one is stronger. And then you can generate a so-called time frequency mask. So this mask could be binary, could also be a soft mask, which is a value between 0 and 1. So I'll show you how effective it is. And the idea is very simple. It's let's just show you the demo here. For example, if you have two speech sources, target and the intrusion. Intrusion means the noise or interference sound. And this is the mixture.
Only the best players enjoy popularity.
And you can see that this is the mixture of two speech sources. So if you know the ground truths of these two speech sources, then you can easily generate a mask. This mask is binary mask, which tells you that at each time frequency point of the mixture, which one is stronger? Is it the target sound? Is it the intrusion, right? So actually, then you can generate this mask and you multiply this mask with the mixture. Then you get this so-called masked mixture. Essentially, this is the separated signals corresponding to, for example, the target sound. Of course, you can change the mask. And then you can hear how good it is in terms of the separated signals.
Primitive tribes have an upbeat attitude.
You can actually completely remove the interference sound, right? So it works pretty well. Of course, here is a bit.
Sorry, just a quick clarification. How does it work out which is the target and the intrusion? Does it derive
Okay,
that?
we'll
Or do you
discuss a bit
specify
more.
that? Okay, thank you. Okay.
Here, just explain the concept.
Yeah. Okay, thanks.
So if you know this mask, you can just multiply it. You get the signals you want, right? But of course, the challenge is how to estimate this.
Yeah.
How to estimate this the mask in this case is a binary mask, right? So there's a lot of methods developed in the literature talking about how to estimate the mask directly from the mixture without knowing the original target speech or intrusion, right? Because this is in practice is unknown. We don't know them. We only have the mixture. But just before doing that, I will give you an example of how to do that. But one of the issues, as you can hear the sound, is if you use this mask, potentially there's a so-called musical noise. You can because the reason is because you use 0 for the area which is belonging to the intrusion, right? But this is a kind of hard mask, which completely get rid of some of the time frequency information at particular time frequency points. But if you look at the original signals here, for example, here, this is a hole here, but there's no hole here, right? So that actually is caused by the mask. So we call musical noise. That is to do with, these artifacts introduced because of this masking. If you have a noise there in the mixture, just now in the sound mixture, we don't have any noise. But if you have a noise like this, then this is like a white noise or this background noise from the fans, for example, in the room. Then you can see that it makes it even worse actually. And in this case, the mask you get, it might be looking like this. A lot of isolated high values in the mask. That actually, if you listen to the sound, there's a kind of musical noise. It sounds like music, but it's an effect in the separated signals, right? So, so there's an idea talking about how to do better. One potential idea is to use this soft mask instead of use a hard mask. Hard mask, either 1 or 0s. You could use a soft mask, and that actually gives you a bit better perceptual quality. But in terms of rejecting the interference sound, it's not as good. There's also a study, perceptual study in the literature talking about how, the difference between these two, binary mask and racial mask or soft mask. And if you look at this visual perceptual domain, right, this is like a disjoint allocation. This is like a duplex perception, right? So basically, each sound source will take part of that in the overlapping area. If the two signals are overlapping in a particular time frequency area, then in the soft masking, each speech source actually estimated one, taking part of the overlapped area. So that is probably more close to what human will perceive, right? They allow the overlapping between the speech sources. And this is how the mask look like in real speech mixtures. This is a binary mask. These two are binary mask. And actually these two visual mask or soft mask. Yeah? And it's sorry, I got it wrong. So on the left column is the binary mask, and the right column is visual mask. But this is actually a different, this one is the ideal scenario where we know the original speech sources, but in practice we don't know that. This actually are estimated from the mixtures. These two are from mixtures. This also from mixtures. And this is actually a different level of errors or noise in the mixture. I mean, you can see that sometimes the masks estimate are not that precise, and if you compare with the original or ideal mask, there's a lot of errors there. So this actually that's the issue. But in terms of perceptual quality, normally the idea, the visual mask or soft mask does better than the binary mask. But intelligibility, actually, the binary mask does better. So there's a kind of trade-off in terms of the quality and the intelligibility, actually. So back to the question you asked earlier, how to estimate the mask. And here I'll give you one example where we actually have two microphone signals, and like a human, we have 2 ears, right? So if we have 2 microphone signals, then we can actually explore the so-called spatial information like interoral level difference and interoral phase difference. That actually, because the sound source is coming from a certain direction, reaching 2 ears, there's a certain delays between the 2 ears when they pick up the signal from the speech sources. Right? There's a time delay. For example, if the sound source from here, then reach this ear earlier and this ear later, right? So there's a time delay. There's also level difference because sound propagates longer distance, decays more, right? So there's we can actually use this information. We could also use a mixed vector. This is similar to the beamforming, where the mixed matrix has this spatial information you can estimate from the mixed matrix. That information can help you to determine the at each time return on a mixture. So now I show this is the broad diagram to show the idea. So this is the original mixtures from left channel, right channel, the 2 ears. And then if you use, for example, short time Fourier transform to convert this into the time frequency domain, at each time frame and frequency point, then you can actually calculate the information, spatial information that I explained. For example, we can calculate interoral level difference and the interoral phase difference by just divide these 2 signals. Yeah, because this is calculated from the sound mixtures, the microphone signals. So we can actually calculate, I just divide these two, we get this information. This is the features we can calculate from this division. And at the same time, we could actually just put these two together. We form a vector, for example. This actually contains also spatial information. We have analyzed the difference between this and these two actually. And then you can actually model these features using some kind of statistical model. For example, you could use a Gaussian mixed model to describe these features like ILD, IPD, and mixed vector. This and then you can actually calculate the posteriors. For example, for each feature, we can use a weight parameter W, WA, WP, WB, and then we also have this posterior we can actually calculate based on the feature information. So how to calculate this? This is a standard technique using, for example, expectation maximization. Because we model these features, then there's a mean and there's also variance. And if they follow this, for example, Gaussian distribution, then we can calculate the mean and variance. At each time frequency point, we can actually calculate that information. And finally, we can come up with a so-called time frequency mask. This is for, we can come up with two masks actually. And then we can multiply these mixtures. Then we can get, individual signals out. For example, if one of the, one of the sources, then, this is the mask actually figure out based on the information here using this, for example, Gaussian mixed models. So, there's a lot of details in the paper, but basically the idea is that to model the features calculated from the microphone signals. And then you can figure out the probabilities of each time frequency point in the speech mixtures belonging to individual speech sources. How likely they're belonging to source 1 or source 2, for example. In this particular example, we have 2 speech sources and 2 microphone signals. So that's how we can figure out that. And we can show you an example how good it is in terms of the modeling. This is the 2-source scenario.
Aim to balance your employee benefit package.
This is the mixture, right? And we have, for example, we can separate them.
Aim to balance your employee benefit package.
Yeah, we can almost completely remove the other interference speech, actually. This is the other one.
I ride the subway, but I haven't enough change.
It does a very good job, right? And of course, if there are more sources, then it gets more complicated. For example, here we have more speech sources.
Aim to balance your employee benefit package.
There are actually 3 speech sources there. We probably couldn't hear that, but and if you use the algorithm to separate them.
Aim to balance your employee benefit package.
And this is.
I ride the subway, but I haven't enough change.
Highway and freeway do the same thing.
Not a great job, but the third one you can also hear that. But in the original mixer, you couldn't even hear the third speech source actually. Yeah, that's the performance for this particular work. Yeah, there's another. Actually, just now I mentioned about this example where you have 3 speech sources. That's actually much more challenging to solve in practice because if you look at the equation here, for example, if we have 4 speech sources and 2 microphone signals, then in this case, if you use a linear system to model that, then you have a 2x4 matrix. And you can see that only 2 observations, how many unknowns? 4 unknowns. And then also this mixed matrix is also unknown. And even in the linear system, this is called underdetermined system, where you don't have unique solutions, or you don't have any solutions, or you could have indefinite number of solutions because this is year post problem. You can't actually calculate the matrix in words to multiply both sides of the equation. There's so many unknowns. And so the key idea in the literature is that we could actually assume that, we assume that the source is following so-called sparsity property. In other words, that when you have the mixtures with multiple sources mixed together, at each time instance, you only have one or two speed sources which are dominant. For example, if you have 4 speed sources mixed together, but at each time instance, you only have one source is dominant or 2 sources dominant. So in this case, you have more chance to estimate the individual speed sources. And that's why we call it sparse representation, right? If the signal is sparse, if the original speed sources are sparse, then we have more chance to separate them. Because in this case, then the underdetermined problem is not converted to a determined problem. And in this case, for example, at one particular time frequency point, only source 1 is dominant, then we can actually ignore the other 3, right? Or vice versa for other time frequency point, we can do something similar. So the problem is that how to identify which time frequency point is dominated by which source. So we could actually use some techniques. For example, there's one technique is that we can actually transform the speech mixture. This is time domain. If we plot them, they actually mix up together, 4 sources here. And they actually overlap with each other. You can't identify any patterns there. But if you use a short time Fourier transform or any other time frequency transform to make it more sparse, then you could potentially see something like this. This is the X1 and X2, right? This is in the time frequency domain. Then you have you can see there's clear patterns there, where actually there are actually 4 sources. And actually this slope here actually corresponds to the column vector here in the mixed matrix. So you could actually identify these.
Yeah, I think you clicked up on accident. You got one of the menus at the bottom here. Yeah.
No, it didn't show me on my.
No.
Okay.
Yeah.
All right. Sorry. So actually, I probably run too slow, right? Okay.
Oh, you just meant
Is it running out of battery?
No. I just thought you meant you were running slow on the computer, but I just
Okay, great. Thank you. So in time-wise, I'm probably running. So I have to run a bit faster. Anyway, so this is the idea for if you have more speed sources than the number of microphone signals. So in this case, we would have to apply additional constraints or assumptions. Otherwise, it's the year post. You don't have any chance to estimate the original speed sources. So this is again is in the conceptual level. But now I come to the second part of my talk. Is we have discussed 3 techniques for separating speed sources from speed mixtures. But if the mixture like the cocktail party mixtures, you have a lot of background noise there and interference sound. Using only the audio signals from microphones might not be enough. So in some scenarios, we have additional information coming from, for example, cameras. And actually, this is also to do with this multimodal perception by humans. Sometimes humans also use the information from the visual signals. For example, especially the deaf people, they cannot hear sound, right? They are very good at doing lip reading. They just look at the shape of the lip, and they can roughly tell what's being said. So there's increasing interest actually looking at the correlations or coherence between the visual signal and the audio signals. Right? So there's a relationship. Can you actually model that and then use that one to help you improve speech separation or speech enhancement? So there's also a lot of work on that. I mean, actually, 1990s actually. There are a lot of work people are doing so-called audiovisual speech recognition, where they actually try to use this, lip reading information or some other visual information to help you improve speech recognition. And then there's a period actually people doing something else, and then actually that's about recently there's a lot of work coming back actually using these deep models like deep learning systems to do that. But anyway, this using this coherence or correlations between the audio and the video information, we could potentially improve the separation quality. So that's the basic idea. Yeah. And if you look at the applications, in some scenarios, you do have these visual signals. For example, if you use the mobile phones to talk to a friend remotely, right? In this case, the mobile phone can look at the lips, not just microphone capture the sound, but also you have the cameras capture the lip movement. So that's why you could potentially model the relationship between them and then use that to enhance the speech signal. And there are some other applications where if you have these visual signals, then you might be able to use this to improve the quality of separation. So, but the key challenge is how to reliably model this audiovisual coherence. And there's a difference between the audio signal and the video signal, for example, in terms of the sampling rate, in terms of the dimensionality. Video signal is we could call 3D signals, right? Because you have 2D images, but also is changing with respect to time, and they have to be synchronized to make it work, right? And also how to fuse the information together. There are many different ways of integrating the audio signals with video signals. And here we just I show you this is video signals. You can see.
Joe took father's green tube bench out.
Not very good quality video, but basically, there's a lip moment actually. And there's also audio signals which can be captured by a microphone. And the lip movement could be captured by a camera. So our objective is to actually try to model the relationship between them, and then to incorporate this information into a speech source separation system. So how to model that? There are different techniques out there in the literature. For example, we could use statistical models, like Gaussian mixed models, as we mentioned for the earlier work. And we could also use sparse representations. And I will explain a little bit more later. And you could also use this deep learning method, which is also a popular method nowadays in the literature. So, the first technique I want to discuss is this to model the coherence between the audio signal and the video signals using Gaussian mixed models, and then to incorporate this information into the speech source separation system. So this speech source separation is a system similar to I already described, right? You using some kind of time friction analysis techniques, you apply independent component analysis, or using the computational auditory scene analysis techniques to do the separation, and then you multiply, you get a reconstruction of the original speech sources. Yeah. So there might be some difference in terms of what you actually process there, but basically this is the audio domain speech source separation. And now the key here is how to model this the coherence between, for example, a typed speech and the associated video signal. Of course, here we are talking about there's a typed speech, right? If I want to separate the voice corresponding to this video signal, then I have this video signal. So the question is how to actually first how to model the coherence between them, and then in the separation stage, we only have the mixture actually. So we don't have the original speech source. So what we have is the mixtures, sound mixtures. We also have the additional signal from video signal corresponding to a target voice, for example. And then can we actually separate out the target voice from the mixture here? So the first step is to model the coherence between, for example, between the audio signal and the video signals. So the first method we take is just using, for example, this low-level fusion, where we have the features calculated from the audio signal and then features calculated from the video signal. And then we put them together, we concatenate them. And then we model these features using Gaussian mixed models, for example. And then we can actually calculate the probabilities, how likely these audio features is corresponding to this video feature. If they give you a very high probability, then we say, okay, these two actually are corresponding to each other. So this is basically, this P is the probability. This can be calculated by using Gaussian mixed model, where we have the features. A is audio features. Could be, for example, MFCC, mere frequency capsule coefficients, could be log spectrogram, whatever features you're using, right? Of course, the dimension might be different. And then the visual features here, in our case, we actually analyze these images. We then capture the mouse region. So mouse region, there's two important parameters. One is the length of the inner, inside of the lips, right? And then also the height. You have to actually outer and the inner contours. Actually, you can use that as features. If you only use the inner contour, then you have the width and also height. That's actually two parameters. You can model the shape of the lip. Or you could also use the four parameters. But in this particular example, we use two parameters, just these two actually. It could be ambiguous for some kind of phonemes. Yeah, that's the information we use to model this coherence. And basically, this is the feature for visual feature, right? We actually calculate the internal lip width and height. Yeah, let's give you a two-dimensional feature. But for audio features, we're actually calculating certain dimensions depending on what features you're using. If you're using MFCC, for example, you could use just 5 dimension or 10 or 15, whatever you like. But of course, the information captured from the acoustic signal will be somehow different. But this is quite efficient or effective for capturing the majority of the information in the audio signals. So that's the feature we have used in this particular work. And then you can actually use a so-called Gaussian mixed models. And you put these two features together, right? You can calculate that, give you this so-called joint feature, audio-visual feature, and then you use these Gaussian mixed models, right? This is Gaussian distributions. You have the mean value, you have the covariance, and depending on how many Gaussian kernels you are using, right? This is, for example, you could use multiple kernels. How many kernels you're using is a user choice, actually. And we have tried, for example, in other papers, we have tried like 20 kernels. So basically, after you do this, you can actually get, for example, this is the features we calculated for R, E, O, U. You can see that the acoustic features, somehow they are different. Of course, there are also similarities there. For example, I and U, they are somehow similar. But these two are quite different. But if you look at the visual features, right, the visual kernel, you can see here, this O and U, they are actually overlapping, right? But if you look at the acoustic features, they somehow quite different, actually. Which means that by combining the audio and the visual features, you could potentially benefit from the complementarity. Because they somehow, for example, in this case, it's very hard to distinguish between O and U. But the acoustic features are more distinctive, actually. And likewise for this one, these two acoustic features, they somehow, similar, but there's more difference if you look at the visual features. Like E is the green one, and U is the this one. Yeah. So you can see that there's they can be well distinguished in the visual domain. So that's the idea. Right? I'm trying to model the coherence between them so that you can better distinguish them from some mixtures. And there are some details about how to do this in the separation process. And in the separation process, what we do is actually, because we have this target video, which is coming from the, how much time I have?
Much.
Already
Oh, yeah, it's 4 minutes till the end of the seminar. We still need some time for questions.
Maybe I should, yeah, I don't have, but basically, we calculate the visual, the features from the visual signals, and then we actually combine with the acoustic signal reconstructed from the speed source separation algorithm. Because here we are using the visual signals to improve the acoustic separation. So basically we are based on the speed separation algorithm, but we try to incorporate this visual information. Here we're actually trying to improve the alignment of the individual frequency component, which we explained earlier. That's the frequency so-called formulation problem. Anyway, we can actually use that to improve speed separation. This is to show a little bit about how we actually use the audio-visual information to help us group the individual source component into individual sources. For example, here, as I explained earlier, the order might be random here, right? And this could be corresponding S1, S2, but this could be S2, S1. So here we have to group them to individual speed sources. How to group them, right? So we can actually use this visual information to help you to make a decision about which source component belonging to which speed source, right? And then we can finally reconstruct the speed sources back to the time domain. Anyway, I need to skip that. Actually, there's a demo showing how we actually group the individual speed source components to the speed sources. Initially they are in the mixtures. Here we have the mixtures actually. They're in the random orders, but finally we group the individual source components into individual speed sources. You can see that, for example, this blue corresponds to one of the speed source, red corresponds to another speed source. Yeah. And another idea is about using audiovisual dictionary learning. I don't have time to discuss now, but I just explain quickly about the key idea. So essentially what we can do is, if you take the audio video streams, right, for example, if they're aligned, then, for example, if you have a word, then you have these lip contours changing with respect to time, yeah? And then this actually is from the video signal. You can capture that. And then you also have the audio signal, which is for example, the log spectrogram. This is time frequency recognition of the audio signal. They're actually corresponding to each other. What we do is we try actually to develop a system that is able to learn these individual audiovisual atoms. We call atoms, means that the components which can be used to build the original audiovisual signals. So in other words, we describe the audiovisual signals as a linear combination of many small signal components. Each component, we call dictionary. Right? We call dictionary. Dictionary contains many words, just like in language we have. Each sentence only contains a few words. In speech, it's similar. It's a signal, but each signal can be decomposed as, signal components. It's a linear combination of multiple signal components. For example, here we have a word pot, right? But there might be another word here overlapping with this one. But essentially, you can actually decompose that into each individual components. And then how to get this one? And we use a lot of training signals, which is we capture, beforehand, like audio and video, we capture them, and then we can train a system, train a model. The model is able to get this dictionary containing many atoms. Each atom is an audiovisual component.
But I hate to stop you, but
Yeah. Sorry for that. I don't have time to probably just escape. I know that's bad. So basically, it's I show you an example about the atoms we learn. Yeah, this is a data set actually developed by CBSP called linear. Actually, this is the audiovisual atom we learned, and then we can actually use this dictionary to help us modify or improve the time frequency mask we explained earlier. Yeah, that time frequency mask we can actually use the visual information as a constraint. There's a different way to do that, but here we only use this visual mask. This is the information which is calculated based on the audiovisual dictionary, and we modify the mask we explained earlier. This is the audio mask, and we can get a better mask. Actually, we can see here. This is idea mask, and this is the audiovisual mask. Actually, of course, in this particular example, we have a lot of noise there in the sound mixtures. And this is the sound mixtures. Actually, this is we can see that this audiovisual mask is more similar to the idea mask in terms of the energy distributions corresponding to a target speech. Yeah, so we can actually that's the okay. There's some demos, but I don't have time to play that. Sorry. So maybe just quickly skip to what is currently happening in the literature. This is the table I borrowed from my former postdoc, where we have this now. In terms of the audio mixtures, now people are more interested in the multi-channel and multimodal. And initially it's a single channel or it's audio only, but now it's audio visual. Right? If you look at this, but of course there are other tasks like speech recognition as well. There's also increasing interest to develop so-called end-to-end system, rather than computing the features and then combine with a learning system. But you could actually directly throwing the audiovisual data into the neural network, and then neural network will learn the features automatically and then make decisions about which sound sources belonging to which time frequency point belonging to which sound source. Yeah. So there's also other development in the literature. It's talking about, for example, general sound instead of only for speech, could be for other sound, music, for sound effect, for example, universal sound. People are studying that. There's also text prompted, language guided sound source separation, and also language guided audiovisual sound source separation. And we have also done a bit work on language queried sound source separation. This is
random. So I've just made two methods. Haven't really created them, but this is how I'm going to deal with them.
And if you input to the system language description, see, and then they will tell you from the mixture. Yeah. To sum up, I have discussed probably too much, and that's why I'm overrun. But basically, the future work I'm interested is to, for example, to look at this highly noisy environment and also universal audiovisual source separation, not just for speech, but potentially also for other sound events in the background. Okay, that's all from me. Thank you so much.
And we're opening